Today's lesson is the first lesson in the series of lessons about the circular motion, and today we will start from learning about kinematics of uniform circular motion. So uniform motion means that our object moves with a uniform speed, uniform the velocity of the magnitude of the velocity remains the same, but the direction of velocity changes. So the object moves in a circular path around its center. The velocity, the magnitude, you can see it's the same, but the direction is different. This one is facing to the right, this one facing kind of like down to the left. But the since magnitude is the same, then we're talking about the uniform circular motion. Now, the acceleration, remember the acceleration is defined as the rate of change of velocity. And because the direction changes, that means that acceleration is actually some value. So it's not just zero. So that means that the object revolving in a circle is continuously accelerating. And the equation for acceleration, A, is written down as the change in velocity, so v2 minus v1 over delta t over time, right? And v2 minus v1 is change in velocity, so delta v over delta t over time. We're looking at the interval of time, which is very, very small. So delta t approaches zero. And we're going to try and figure out what is the instantaneous acceleration, because we know we can figure out our instantaneous velocities. And for that, I'm going to redraw this diagram slightly so that it looks like this. The object moves in a circular path, and during some time delta t, what the object does is it moves from point A, so I'm going to connect the center with point A somewhere here, to point B. And we're looking at some time delta t that is short, but it's not zero yet. So let me label this point is point A, this point is point B. And what happens with velocity is the vector of velocity is pointing strictly to the right. It is tangent to our circle, and this one is pointing this way. The magnitude is the same, and I'm going to label that the angle between those two instances is theta, or rather delta theta, so the change in angle. This is the radius, and radius. We have our v1, we have v2, those are the velocities. And then the change along the arc, so this change, this one, is delta L. So delta L is the distance that our object is going to go through along the arc, because it moves in a circular motion, from point A to point B in our time delta t. Now let's look at some vectors. So we have our vector v1 and vector v2, and we are going to take v2 and subtract v1, and that is going to give us a change in velocity. We're going to call it delta v, vector v. In other words, if I manipulate with both sides, I can say that v2 equals v1 plus delta v if I add v1 to both sides. And let me draw another diagram to demonstrate what is happening when delta t becomes very, very small. So I will have my vector v1 facing this way. Okay, should have been horizontal. It's okay. And then vector v2 is going to be facing this way. And then when time is very, very small, then this vector v, it's actually going to be, well, those two vectors, v1 and v2, they're going to be nearly parallel. So my angle delta theta is going to be also getting closer and closer to zero, right? So we're looking at the instantaneous acceleration, instantaneous velocity, what is happening at an instant. So this angle is basically zero. So this vector delta v is going to be perpendicular to both of those, v2 and v1. And in that case, we can say that, well, approximately, we can say that v is the same as v1 and the same as v2. So I'm just going to drop those sub-indices and rename my. So to specify again, v1 and v2, they have the same magnitude. So see, I'm not labeling them with the vectors. It is the magnitude of vector v1 and v2. Now take a look at this triangle that we have here and this triangle that we have here. If I were to draw a chord AB, then my triangle, let me label this point C. So my triangle CAB is going to be similar to this triangle that I have here. V1 and V2, they have the same magnitude, so V, and then I have my angle delta theta, right? So these two triangles, they are similar, which means that from similarity, I can say that delta V over V, so delta V is this side, the magnitude of this side, and no vector here, over V, over the magnitude of this side, has to be equal delta L. So technically it's going to be this, the length of this segment here of the chord AB, but it's getting very, very close. It's becoming very close to the length of the chord. So I can say approximately equals delta L over R. Right, so again, delta L is the length along the chord, and then the length of the chord AB is very close to that. So we can say that those two are approximately equal. Now, when delta T approaches 0, so our time is getting much, much smaller, so approaches 0. In that case, delta L is actually going to be equal the chord length AB, and we can write down that delta V equals V over R. I'm multiplying both sides by V times delta L. So now they're equal. They're going to be identical. And to get the acceleration, to get the centripetal acceleration, is we're going to do this. We're going to take our delta V that we said before. We're going to divide it by delta T. Okay, and then delta V, we just got the formula, V over R times delta L, and I'm going to put delta L over delta T kind of like separately. So it's V over R times delta L over delta T. Well, look at this. Length over time. That is the same, so this guy is the same as the linear speed. So it equals V as well. So here's what we get. We have that our acceleration is V times V, which is V squared. So AR is going to be equal V squared over R. V squared over R. Let's take a look back at this diagram. So where we drew V1 and V2 and our vector delta V. So if I were to redraw it on this diagram, so when they're very, very close, then delta V is going to be pointing, it overlaps with my delta L. So that vector is going to be pointing towards the center of the circle, right? It's going, those two are parallel, nearly parallel, and then V is pointing this way, delta V. So since delta V is pointing towards the center of the circle, that means that our acceleration is also going to be pointing towards the center of the circle. The object is trying to fall down, so to speak, on the to the center of the circle. And that's why this acceleration is called centripetal acceleration or radial acceleration. Let me write it down for you. So this is how you spell centripetal acceleration or radial acceleration. So to summarize, if you have an object that is moving in a circle of radius r at a constant speed v, then the acceleration is going to be pointing towards the center of the circle. So the direction of the acceleration is towards the center of the circle, and the magnitude of acceleration is going to be equal v squared over r. Let's do it. Okay. Um, 150-gram ball at the end of a string is revolving uniformly in a horizontal circle. ТНД 149. Given second revolutions per second. Значит, 1 revolutions per second. 1 over 2. 2 is 0.5 seconds. Distance is circumference. Divided by r. And then now speed of the moon in orbit. G 0.03 G. Okay, approximately 2.72. 2.72 AR equals 2.72 times 10 to negative third meters per second squared.